Humanity's journey into space began with a fiery roar, propelled by the raw power of chemical rockets. For decades, these magnificent machines have been our only ticket off Earth, pushing us to the moon, sending probes to the edge of our solar system, and establishing a permanent presence in low Earth orbit. But their limitations are clear. Immense fuel requirements, colossal expense, and the sheer inefficiency of throwing away most of the vehicle after each launch. The future of space travel demands something more. It requires breaking free from the constraints of Newton's third law as we know it today, moving beyond the brute force of combustion, and embracing revolutionary technologies that will unlock the cosmos in ways we can only just begin to imagine. This isn't just about faster trips to Mars. It's about making the entire solar system a backyard, and perhaps one day venturing to other stars. One of the most immediate and promising advancements beyond traditional chemical propulsion is electric propulsion. Unlike rockets that burn fuel, electric thrusters use electrical energy to accelerate a propellant, typically a noble gas like xenon, to incredibly high speeds. Think of it like a continuous gentle push rather than a powerful short burst. While their thrust is tiny, often no more than the weight of a sheet of paper, they are vastly more fuel efficient. Over long periods, this low thrust builds up immense velocities. Ion thrusters are already in use on missions like NASA's Dawn spacecraft, which explored Vesta and Ceres, and will power elements of the Lunar Gateway. They are ideal for deep space missions, where speed isn't about the initial kick, but about sustained acceleration over months or years, dramatically reducing the amount of propellant needed. Taking electric propulsion to the next level are concepts like the Vinjh engine, variable specific impulse magnetoplasma rocket. This advanced plasma propulsion system heats propellant to extreme temperatures, creating a plasma, then uses magnetic fields to accelerate it. Vinjh promises higher thrust than current ion engines while maintaining excellent fuel efficiency, potentially cutting travel times to Mars from months to weeks. But what if we could move without carrying vast amounts of propellant at all? This is where solar sails come into play. Imagine a spacecraft unfurling colossal, incredibly thin, mirror-like sheets in space. These aren't sails catching wind, but rather catching photons, tiny particles of light from the sun. Each photon, though massless, carries a minute amount of momentum. Billions of photons bouncing off the reflective surface generate a continuous, albeit minuscule, push. Over time, this constant solar radiation pressure can accelerate a spacecraft to incredible speeds without a single drop of fuel. Missions like Japan's Icaros and the Planetary Society's LightSail have already demonstrated the viability of this ancient yet futuristic concept. The challenge lies in deploying and controlling sails that can be football fields or even square kilometers in size. Moving further into the realm of advanced concepts, we encounter nuclear propulsion. While nuclear fission has been used for power generation on spacecraft for decades, nuclear propulsion systems would directly use the energy from a nuclear reactor to generate thrust. There are two main types: nuclear thermal propulsion, NTP, and nuclear electric propulsion, NEP. NTP works by superheating a propellant, typically hydrogen, with a nuclear reactor and expelling it through a nozzle, achieving twice the efficiency of the best chemical rockets. NEP, as the name suggests, uses a reactor to generate electricity, which then powers high-efficiency electric thrusters like ion engines. Nuclear propulsion offers faster transit times and significantly increased payload capacity, making it a game-changer for human missions to Mars and beyond. Though safety and public perception remain significant hurdles, beyond our solar system, the distances become truly mind-boggling, requiring speeds approaching a significant fraction of the speed of light. Here, technologies become even more speculative. A beamed propulsion, for instance, envisions a powerful laser array on Earth or in Earth orbit, firing a concentrated beam at a light sail attached to a spacecraft. This external energy source could accelerate tiny probes to unprecedented velocities, potentially reaching nearby star systems in decades rather than millennia. Breakthrough Starshot, for example, aims to send gram-scale probes to Alpha Centauri within a human lifetime using this very principle. Then there's the concept of interstellar ramjets. This sci-fi staple imagines a spacecraft scooping up diffuse hydrogen atoms from the interstellar medium and using them as fuel for a fusion reaction. While still theoretical, it offers the tantalizing prospect of a spacecraft that can refuel itself mid-flight, potentially sustaining journeys across vast cosmic distances. And what about the ultimate dream? Faster-than-light travel. The Alcubierre warp drive, a concept derived from Einstein's theory of general relativity, proposes that a spacecraft could travel faster than light by warping space-time itself. Instead of moving through space, the drive would contract space in front of the vessel and expand it behind, creating a warp bubble that carries the ship along. Inside the bubble, the spacecraft itself wouldn't be moving faster than light, thus seemingly bypassing Einstein's speed limit. While mathematically consistent, this concept currently requires exotic matter with negative energy density, something we haven't discovered and aren't sure even exists. It remains firmly in the realm of theoretical physics, but it highlights the boundless imagination driving future propulsion research. Finally, we consider infrastructure. Imagine a space elevator, a giant cable stretching from the Earth's equator into geostationary orbit. Instead of rockets, climbers would ascend this cable, powered by electricity, carrying payloads and people into space at a fraction of the cost and with vastly increased safety. While the materials required for such a structure are currently beyond our engineering capabilities, a cable strong enough to support its own immense weight would need to be stronger than anything known. The concept offers a vision of truly routine, affordable access to space. The future of space travel is not a single monolithic technology, but a mosaic of groundbreaking innovations. From the steady push of ion thrusters to the mind-bending possibilities of warp drives, each concept pushes the boundaries of engineering and physics. As humanity looks out at the stars, the next chapter of our cosmic journey won't be defined by how high our rockets can reach, but by the ingenuity that propels us truly beyond.